Let's solve just one more open system continuity problem, and then we'll move on. Air flows through a duct with steady state data supplied in the schematic below. Assuming ideal gas behavior for the air, determine the inlet volumetric flow rate in cubic feet per second and inlet mass flow rate in pounds mass per second. If you can determine the volumetric flow rate and the mass flow rate at the exit, evaluate them. If not, explain. So here we have a rectangular duct, constant area duct, with air flowing through it. And we're given the velocity, temperature, and pressure at the inlet, and also a pressure at the exit, which is slightly less than the pressure at the inlet due to the pressure drop in the duct. Here's what we know. That at state 1, we have a velocity of 3 feet per second, a temperature of 95 degrees Fahrenheit, and a pressure of 16 psi. At the exit, the pressure is 15 psi, and the area is the same as at the inlet as it is at the exit, and that's just 4 times 6 square inches. We'll model this as an open system operating at steady state, and we'll consider the air to be an ideal gas. We want to find the volumetric flow rate at the entrance in cubic feet per second, also the mass flow rate at the entrance in pounds mass per second, and then we want to find the same values at the exit if we can. So let's solve this problem. We know the mass flow rate at the entrance is the volumetric flow rate divided by this specific volume. And we know we can use the ideal gas law to find specific volume, and it simply says P1V1 is RT1. So let's rearrange and solve for specific volume at state 1. That is the gas constant, which is the universal gas constant of 1545, divided by the molecular weight of 28.97, yielding units of foot-pounds force per pound mass R. We're going to multiply by the absolute temperature, which is 95 degrees Fahrenheit. We must add 460 to that to get Rankine degrees. We're going to divide by the pressure, which is 16 pounds force per square inch, and we'll convert square inches to square feet. And we calculate that the specific volume at the inlet is 12.847 cubic feet per pound mass. Now we can calculate the volumetric flow rate at the inlet, which is just the area of the inlet times its velocity. And the area is 6 inches times 4 inches. We'll convert that to square feet. And the inlet velocity was given as 3 feet per second. So that gives us a velocity of, a volumetric flow rate at the inlet of 0.5 cubic feet per second. Now we can evaluate the mass flow rate at the inlet. The mass flow rate at the inlet is just the volumetric flow rate divided by the specific volume. We just calculated the volumetric flow rate at 0.5 cubic feet per second, and previously we calculated the specific volume at the inlet of 12.847 cubic feet per pound mass. That gives us a mass flow rate going into our system of 0.0389 pounds mass per second. So now the question before us is whether or not we can calculate the volumetric and mass flow rates at the exit. Well, we can certainly calculate the mass flow rate at the exit. The mass flow rate at the exit is simply the mass flow rate at the inlet. There's no other place for the mass flow rate to go. So we know that the mass flow rate at state 2 is the mass flow rate at state 1, which is 0.0389 pounds mass per second. How about the volumetric flow rate at the exit? Well, we have two expressions for volumetric flow rate. One is the mass flow rate times the specific volume at the exit. That will give us the volumetric flow rate at the exit. Or we can use the area at the exit times the velocity at the exit. Well, let's look at this first expression, the mass flow rate times the specific volume. We know the mass flow rate. Do we know the specific volume? Well, not yet, but we could use the ideal gas law to calculate it. It's just the specific volume is RT over P. We know P2. The problem is we don't know T2. So the temperature of the exit is unknown. So that leaves V2 unknown, and that means I cannot use this expression here to calculate the volumetric flow rate at the exit. How about this expression? The volumetric flow rate is just area times velocity. Well, the exit area is known. It's the same as the inlet area, but the velocity at the exit is known. And without the specific volume, I can't calculate the velocity. So without the temperature or velocity at the exit, the volumetric flow rate at the exit cannot be determined.